Well, thank you. I really want my mom to see that video. That's pretty impressive. I'm really honored to be inducted into the Silicon Valley Engineering Council Hall of Fame and to be in the company of such luminaries as Bill Hewlett and David Packard. I'd like to thank a lot of people who were involved in this. As everybody knows, engineering is a team sport and nobody wins or loses on their own. First of all, I'd like to thank Sharif and Fred and the leadership of the Silicon Valley Engineering Council for recognizing me and for actually doing the whole Hall of Fame. I think it's a great service to the community. In thanking people, I'd like to start with my parents. From a very young age, they instilled in me a love of science and engineering and learning, and taught me the value of hard work. I'd like to thank my family, most of whom is here tonight, my loving wife Sharon, and my daughters Katie and Jenny, who are here, my daughter Liza, who couldn't make the drive up from LA because of the weather. They've really supported me over the years and have been very tolerant of long hours spent on engineering projects of various kinds. The development of stream processing and its evolution to GPU computing were not an individual effort. They involved a very large team. Pat Hanrahan was my partner at Stanford on the streaming supercomputer project that really kicked everything off. Many of the students on the project, some of whom are here at the alumni table tonight, were really very, made pivotal contributions to that. In fact, teaching both in the classroom and mentoring of PhD students has been probably the most important thing I've done in my life and the most rewarding contribution of my career. Since I started as assistant professor at MIT in 1986, I've supervised 56 PhD students. Several of them are here at the alumni table. I thank them for coming and also for working with me. They've contributed a lot of energy, ideas, and fresh viewpoints to my work over the years on networks, circuits, parallel computing, as well as the work on stream processing that led to GPU computing. Once the work was done at Stanford, the translation of stream processing into GPU computing was also a huge team effort. It really started with my longtime friend and ski buddy, John Nichols, who invited me to give a lecture on stream processing at NVIDIA, probably in the late 2002, it might have been early 2003. And then he had John Danskin, who was one of the VPs of engineering at the time, hire me as a consultant to work on the architecture of the NV50, putting in a lot of features that were important to make it a good vehicle for computing and for running compute shaders. And of course, everything transfers with human beings. Ian Buck, who was a really key student on the streaming supercomputer project, and who had developed the programming language Brook, which we used to program that machine, was hired at NVIDIA in 2004 and took all the learnings of that project to develop the CUDA language, which basically led off the revolution in GPU computing. And David Kirk, who was the chief scientist of NVIDIA at that time, and Wenmei Hu, a professor at the University of Illinois, were evangelists. They took that and taught teachers courses around the country to basically spread the religion of GPU computing, and it really took off. A lot of credit goes to Jensen, who's here tonight, to have the vision to invest in GPU computing and to stick with it for many, many years before it actually made business sense. The cost of supporting the philosophy we had of CUDA everywhere, to put the facilities for GPU computing in every GPU we sold, was not inexpensive, but ultimately it really changed the face of computing and enabled modern deep learning. GPU computing was the spark that enabled the current revolution we're all seeing. I'm sure all of you have at least spent one weekend day playing with ChatGPT. It turns out that most of the algorithms were around since the 1980s. Deep neural networks, training them with stochastic gradient descent and backpropagation, were all published by 1989 or earlier. And most of the large data sets on which these networks are trained were available by the early 2000s. And so you can think of that as the fuel in the air. The spark that ignited the current revolution in GPU computing was having a computer with enough power to train a powerful enough network with a large enough data set in a reasonable amount of time. And that took the evolution of GPU computing to do. My own pivot from doing high-performance scientific computing to AI happened with a breakfast I had with my Stanford colleague, Andrew Ng, in 2010. And he was telling me about the work he was doing at Google finding cats on the internet. So I recruited Brian Catanzaro, who's here somewhere, he was a programming language researcher at the time, to work with Andrew and replicate that experiment, but using 48 GPUs instead of 16,000 CPUs. And the software that came out of that project turned into cuDNN and really laid the foundation of the huge amount of software that now makes it easy for people to take an NVIDIA GPU and run deep learning, and makes NVIDIA GPUs the engine of choice. So since those early days of GPU computing and deep learning, our focus has really been on efficiency, Despite some people denying it, Moore's law is dead. It's not even twitching anymore. And we can no longer really count on semiconductor technology to give us regular improvements in the efficiency of our machines. Instead, we have to apply real engineering. And it's taken optimized number representations, exploiting sparsity, and specialized instructions to double the efficiency of GPUs on deep learning every year since 2012. It's given us a 1,000x increase in the past decade. And we're working hard on innovations to keep that going. We prototyped some of these in a chip that we described last year at the VLSI Circuit Symposium that achieved 100 teraops per watt efficiency. And to put that in perspective, that's about 10x the efficiency of Hopper, our latest GPU. So we've got at least 3 more of those doublings pretty well put away if we can simply translate that prototype into the core GPUs. And we see that it gets harder every generation, but there's a lot more yet to come, and I think we have a lot more doublings even beyond that. So going forward, I'm very excited that the principles of stream processing that led to GPU computing and the specialization that has fueled the current revolution in deep learning can be applied to a lot of other computations. In our Hopper generation GPU, we added an accelerator for dynamic programming that's really useful in accelerating bioinformatics computations. In the future, we envision that a lot of other demanding computations, such as continuous and discrete optimization, can also be accelerated via special purpose hardware and accelerated computing. So to conclude, I'm really honored to be inducted into the Silicon Valley Hall of Fame. The work for which I'm being recognized is not my own. It's part of a large team effort. Many faculty and students participated in the stream processing research at Stanford, and a very large team at NVIDIA were involved in translating this research into GPU computing. It's a really exciting time to be a computing engineer. I hope the son of our MC decides to be a computer engineer, not just an engineer, because it's a time when you can have an enormous amount of impact. The future is bright, with a lot more demanding applications waiting to be accelerated using the principles of stream processing and accelerated computing. So thank you all again.